Okay, folks, we can get started. So I am aware of two groups that took their cricket chirper outside and attempted synchronization. One group with some kind of sort of partial success, as I understand. The other group with a little bit harder to tell, inconclusive results. Did anyone else give it a shot? Just out of curiosity? Okay, well, you might consider doing so if you care to. Some quick things that I'll mention before I get into today's content is I put an announcement on Canvas that hopefully you all saw, but my plan for essentially the rest of the semester is I'll just open up the lab when I get on campus, which is usually somewhere around 9, sometimes a little bit before, sometimes a little bit after. And it'll remain open until either until lecture or until 2300 comes in there, which means a couple of hours every morning. I won't necessarily be in there that whole time. I have to do some other stuff during that time, but if folks want to come in and work independently during those hours, that's totally fine. And then the other thing that I'll do is I'll maintain the same Monday, Tuesday open hours that we had last week. So Mondays 3 to 5, I think were the hours, and Tuesdays 11 to 1. I'll make sure that the lab is open. So I'll open it up, sometime around 3 today if folks would like to come in and start getting ahead on lab 2. Any questions from anyone before I get into stuff? Okay, so my plan today is to actually talk about the stuff that I intended to talk about last time. In particular, I want to talk a little more technically about the implementation of the Boids algorithm. And to help talk through this, I'm going to go to the web page associated with the Boids algorithm. And I will just remind you, very, very briefly, I'll remind you that to get Boids to work, what we're going to do is instantiate a whole bunch of individuals, a bunch of Boids, and each of those Boids will follow a simple set of rules for updating its position and velocity between frames. And the emergent phenomena that we'll get when all of these Boids follow the rules that I'm about to describe is flocking behavior. And then on top of that flock, you'll implement a version of the algorithm that Tom Seeley helped discover that describes how these large swarms are biased to go in a particular direction by a small subset of the group. So I want to talk today in detail about how we're actually going to implement this. And the way that I'll start is by talking about what state do we need to keep track of for each Boid. And each Boid is you will need to keep track of 4 states for each Boid. In particular, each Boid is going to have an X position and a Y position, and each Boid is going to have an X velocity and a Y velocity. And then each frame, you'll run the algorithm that we'll describe here in a moment to update each Boid's X and Y velocities, and then you'll use that Boid's updated velocities to update its position. Incidentally, people in the waiting room. The relevant units here, what's the relevant units for position? Pixels. How about velocity? Pixels per second would work. I think an easier unit to use is pixels per frame. So you'll keep track of position in units of pixels. So a particular Boid could be if it's on the VGA screen, and incidentally these Boids are allowed to leave the screen and come back. But if it's on the VGA screen, it'll have a position in an X range of 0 to 640, in a Y range of 0 to 480, well 0 to 639, 0 to 479. And then its X and Y velocities, we'll talk about this, but we'll constrain those to be somewhere within the range of like 1 to 3 pixels per frame. And we'll use a fixed point data type to represent all these things for a couple of reasons. One is it's faster than floating point. But for this application, we do need a data type that allows for fractional resolution. And the reason for that is if you think in particular about the velocity, we would like for Boids to be able to have velocities that are less than 1 pixel per frame. So we would like for a Boid to have a velocity of, say, a half a pixel per frame. And what that will mean is that for 2 subsequent frames in a row, the Boid will be drawn to the same pixel. And then on the next frame, it'll be updated to its updated pixel. But by maintaining fractional resolution for our velocities, it allows for us to draw that boid in the new pixel at the correct frame. So this is really, really reminiscent of direct digital synthesis, actually. Remember in direct digital synthesis, we were thinking about that accumulator variable as keeping track of which index of the sign table to access. And the way that we were thinking about this was the top 8 bits of the accumulator variable were keeping track of the integer value of which index to access. So when we index into the sign table, we right shifted by 24. So we index into the top 24 bits. And then the remaining bits were keeping track of fractional amounts of index. This was what was allowing for us to move to the next index at the correct interrupt. Almost the identical concept here, where for our velocities, we want to be able to draw to the same pixel for the correct number of frames and then move to the next pixel on the right frame. Fixed point allows for us to do that without sacrificing a whole bunch of CPU time to do arithmetic. Okay, so let's talk through this algorithm. And I'm going to talk through it one step at a time. As I mentioned, each of these boids is essentially following 3 rules. One is separation, defending its personal space. Another is alignment, aligning itself with its neighbors so that it doesn't leave the group. And then the third is cohesion, which is a gentle tendency towards the center of mass of its local neighbors so that they remain cohesive. So let's start by thinking about separation. So last time I briefly mentioned that for each boid, there are 2 relevant distances that boid cares about. There's a distance that's relatively close to it, represented by this inner circle that we're going to call its protected range. This is its personal space that it tries to defend. And then there's a further distance represented by this exterior circle that we're going to call its visual range. And this is as far as this particular boid can see. So this boid will try to move away from any boids that come within its protected range. It will try to align with and move towards the center of mass of boids in its visual range. And any boid outside of its visual range might as well be invisible. A particular boid can't see beyond its visual range. This is just like in nature, incidentally, where if you have a flock of starlings, a particular starling in that flock can only see so far. It doesn't have knowledge of what every bird in the whole flock is doing. It can only see what its neighbors are doing. So just like that, each boid can only see what its neighbors are doing. So let's talk about this first rule, which is separation. The way that a particular boid will enforce this rule is summarized here. So for a particular boid, so we're going to go through and run this process for each boid, but suppose that we're updating the velocity and position for a particular boid. For that particular boid, we'll start by zeroing a couple of variables that maybe you call something like close dx and close dy. And in those variables, we're going to store information about the x and y positions of any boids that are too close to this boid that we're updating. So we zero these variables, and then we loop through every other boid in the flock, and we access the position of every other boid in the flock and determine whether or not that other boid that we're looking at is within this protected range. If it's not, then we just go on to the next boid. If it is within this protected range, then we increment each of those variables that we zeroed, close dx and close dy, by the difference between our x position and the other boid's x position, and the difference between our y position and the other boid's y position. Once we've gone through every boid, we then update our velocity by the accumulated values for the difference between our own x and y positions and those of every other boid in our protected range, multiplied by a factor here that we're calling the avoid factor. I have a suggested value for this, but what we're going to find at the end of this is that the velocity update ends up looking a whole lot like a weighted average. So there are contributions to your velocity update that come from your tendency to want to separate from those that are too close, your tendency to want to align with your neighbors, and your tendency to want to move towards the center of mass of your neighbors. And by changing the avoid factor here and the similarly named factors for those other 2 tendencies, you can play with the relative weights of these velocity updates. And in the lab write-up, I have some suggested values that will give you a flock that looks right. It looks organic. But in any case, so we update our own x and y velocities by those accumulated variables multiplied by this avoid factor, which is our weight for this particular contribution to the velocity update. There questions about this? So suppose that we have our flock swarming around, It's doing the stuff that we were looking at last time. And we took the avoid factor and turned it up really high. What would be the emergent change in behavior that you would expect to see in the flock? Yeah, I saw your hands moved. You got the right idea. A poof out. They would care more about protecting their personal space. So what you would likely see is the distance between all the boids in the flock would increase a little bit. They would have a less tendency to go within each other's protected ranges. If you were to turn that way down, then the boids would not care at all about getting too close to one another, and you might see the flock get a little bit more aggregated. So that's separation. In addition to trying to get away from boids that are too close, each boid also tries to align with all the boids that are outside of its protected range but inside its visual range. And it does this in the following way. So similar to before, for a particular boid that we're updating, we start by zeroing a few variables, which you might call something like x velocity average, y velocity average, and neighboring boids. And those names suggest exactly how we're going to use those variables. And then similar to before, for a particular boid, we loop through every other boid in the flock, and we ask, is this other boid that's in the flock farther away than my protected range, but inside my visual range? That is to say, is it within this disk here? If it is, then we increment the x velocity average by the other boid's x velocity. We increment y velocity average by the other boid's y velocity. And we increment the number of neighboring boids by 1, which is to say we've counted one additional neighboring boid. And then, once we've looped through all the other boids, if we have any neighboring boids, that is to say, if this neighboring boid's value is greater than 0, then we divide x velocity average and y velocity average by the number of neighboring boids that we have. We are calculating the average x and y velocities of our neighboring boids. And then, with this information, we update our own x and y velocities. And we do so by subtracting the average x and y velocities of our neighboring boids, by subtracting our own x and y velocities from the average x and y velocities of our neighboring boids, and multiplying by a similar weighting factor. So this is analogous to the avoid factor that we were just looking at before. This is the contribution to that weighted average that comes from alignment. How much do the boids care to align with their neighbors? If you turn this way up, what's the emergent behavior that you expect to see? It's kind of inorganic looking, but what you end up seeing is that the whole flock moves like this. Every boid has essentially the same x and y velocity, and they kind of bounce around the screen. If you turn this way, way down, then your flock becomes much more chaotic because none of the boids care to try to align their velocities with one another. They might still care to protect their personal space if you have that avoid factor turned up. They might, as we'll talk about in a moment, still care to tend towards the center of mass of their neighbors. But if you turn this all the way down, say to 0, then they will not care to align with one another. I'm asking you to think about these things incidentally because if you can hypothesize the behavior of the flock that you would expect if you zero any of these things, it's helpful for debugging, right? Say you implement this algorithm, it doesn't look right. A strategy by which you can start to figure out what's going wrong is zeroing out the contributions from, say, avoiding other boids in personal space, from alignment and from separation and so on, and seeing where things start looking weird. Question?
What if we have a large visible range? If in that case the matching factor is larger than 0, would it be like the first case you described that where they're all synchronized with each other, they're moving the same speed? And because that would be a stable situation for this model, right?
It would be. So your question is, what if the visual range were very, very large? Say it. took up the whole screen.
Yeah.
So there'd be a couple consequences of that. One of the consequences is with the suggested parameter values written up here in that video that we were looking at last time, with the visual and protected ranges set as they are, the flock will occasionally split into separate groups and then coalesce. If you were to make the visual range very, very large, the expectation is the flock would never split up because every boid becomes a neighboring boid to every other boid. So they're all making velocity and position updates influenced by everybody else. The other consequence of this is the amount of computation required to do a frame update is going to increase radically because now every single boid has to account for information, has to do arithmetic associated with the position and velocity of every other boid in its visual range. If that includes every other boid in the flock, then the amount of computation associated with updating the flock increases a lot.
Yeah. And the one comparison is taking approximately 1 cycle, right? Between two numbers.
A comparison is cheap. If it's not 1 cycle, it's darn close.
Yeah.
Yeah. There's another question? Yeah.
Yeah, is there possibly a better way to find all the neighboring boids rather than like looping through every single boid, or is that just really?
Ooh, I'm glad you asked. So I was going to talk about this, but let me jump ahead a little bit. So what's the point of this lab pedagogically? Like, why do I like this lab as a teacher of a class like this? What I am hoping that this lab will teach is optimization strategies. So what I have at the bottom of this webpage that we'll look at here in a few minutes is some pseudocode that describes the most straightforward, that is to say, unoptimized implementation of this algorithm. But this algorithm is full of opportunities to speed things up. So this search for other neighboring boids is a good example where if every boid looks at every other boid, then the search part of this algorithm is n squared complexity. You can get clever and make that better. I think you can make it as good as n log n. I think. If you make the observation that if I'm boid A and I'm looking at boid B, then by the time I get to boid B, I don't have to have boid B look back at boid A. I can update them both when they're looking at each other. And if you account for that, then you get considerable speed up in the search part of this. The other thing that you are allowed to do in this lab is, this is a computer graphics lab, and a joke that I heard from Bruce is, in computer graphics, if it looks right, it is right. So in your checkout, what I will ask to see is flocking behavior, something that looks like the behavior that we were looking at last time, and I'll ask for you to demonstrate, the biasing that we talked about last time. If you find ways to cheat in this algorithm, that's allowed. So you can look through this. What you'll be encouraged to do is implement the algorithm and first of all, just get it working. Get a naive implementation working. And then study it and ask yourself, what are the expensive steps here? Are there any arithmetic steps that are particularly expensive for which I could come up with a reasonable but fast approximation? Things like the search mechanism. Can I optimize that? And so long as your cheats lead to a behavior where I can't tell the difference, you're good. So it's addicting. This lab's really, really addicting because you'll get it working. And then part of the reason that I like this particular algorithm for this particular lab is it is filled with such opportunities. And my only requirement is you have to trick my brain. And my brain's not that different from your brain. So you'll know if the requirement's being met or not, because if you look at it and it doesn't look right, it doesn't look right. You can't really trick yourself. Incidentally, one of the things that is absolutely required in order to make that illusion work is frame rate. So I am requiring 30 frames a second. Has to be 30 frames a second. If you start to drop below 30 frames a second, your flock will stutter and doesn't look organic. The organic illusion has to be maintained through the entire demonstration. Question?
Is it possible to make a 15 frame per second and just making a minimum purity.
Yeah, sure. It has to look smooth. It has to look. For me, for this illusion to hold 30 frames per second looks really good. It holds. So the mindset that you will be adopting in this lab is that of like a, I don't know, maybe like a race car engineer, you know, someone who is obsessed with shaving mass. What you will be doing is looking at this algorithm and getting obsessed with shaving cycles. Anywhere you can save cycles, you will try to save those cycles. Buy the highest end McLaren, it doesn't even have door handles. It's just rope. You pull on the rope, right? So that's the kind of mindset that you're getting into. Okay. The third contribution to the Boids velocity update is cohesion. So in addition to trying to move away from any boids that are too close and trying to point in the average of the direction of its neighbors, each boid also steers gently towards the center of mass of its neighbors. And it does so in a way that's really similar to the alignment. So it starts by zeroing a series of variables. You might call them x position average, y position average, and neighboring boids. And then, as before, every boid looks at every other boid. In the event that it finds a boid outside of its protected range, but in its visual range, it then increments the x position average and y position average variables by that other boid's x and y positions, and increments the number of neighboring boids by 1. And then, just like before, if the number of neighboring boids is greater than 0, it divides that accumulated value by the number of boids. It computes the average. And then the change in its own velocity that happens as a consequence is it will subtract its own x and y positions from the average x and y positions of its neighbors, multiplied by another one of these weighting factors, the centering factor, which, as before, describes this particular, it describes the cohesion contribution to this weighted average that updates the particular boid's velocity. Okay? And then there are a couple of other rules that I will ask for you to follow that just help with the illusion. First is the boids have to stay on the screen, or they have to at least come back when they leave the screen. So the way that we'll implement this is in week 1, you'll be asked to describe some boundary that's inside the edges of the VGA screen. And when a boid leaves this boundary, it'll gently start to turn back around and come back towards the center of the screen. So, for instance, if the boid x velocity, or boid x position rather, is less than the x margin, that is to say it's over here, then we will increase its x velocity by a little bit. We'll start to turn it. This is positive velocity and negative velocity, right? So we'll start to turn it back towards the center. And likewise on all the other sides. And that turn factor is something that you can play with. I have a suggested number here that gives a radius of curvature that I think looks organic. If you make that too high, you end up with billiard balls bouncing off the walls. Doesn't quite look right. If you make that too low, they'll leave the screen and just kind of never come back, or they'll take forever to come back, right? So some happy medium between a nice organic looking radius of curvature or between billiard balls and never coming back. And the number I suggest, I think, is about right, but you can play with it if you would like to. The other thing that I'll just mention, well, actually, I'll get to that in a second. And then the last thing that I'll ask for you to implement is, or no, there's 2 more things I'll ask for you to implement. The next is bias. So you go through this whole process and you compute the boid's new velocity that is a function of moving away from boids that are too close, aligning with neighbors, and tending towards the center of mass of neighbors. So you go through and you come up with this new x and y velocity. And then if that particular boid is in one of your scout groups, right? If it is one of the bees that has gone out and looked for new hive locations and comes back and has a preference about where it would like for the whole colony to go, then it will have a bias. And it could have a bias either towards the right side of the screen or the left side of the screen. So one of the last steps that you'll implement here is you'll say our x velocity is going to be equal to 1 minus that boid's bias value times the x velocity that we've just computed, plus that bias value times 1, which would be a preference towards the right side of the screen, a positive x velocity. So if this bias value is 0, that is to say the boid is unbiased, then the boid's x velocity is equal to 1 minus 0, that's 1, times the x velocity that we just computed, plus 0 times 1 is 0. So in the event that it has no bias, then the velocity remains unchanged. In the event that it is completely biased, the bias is 1, then this term goes to 0, and that zeroes out the velocity that we've just computed, and so the boid's velocity gets updated to just 1. That is to say, it's completely ignoring everything its neighbors are doing. All it wants to do is go towards the right side of the screen. It's no longer looking at any neighbors at all. And if it's somewhere in the middle, which is the realistic place for it to be, then it might have a gentle preference towards this side of the screen, but it still doesn't want to leave its neighbors behind. And what you'll find is that this will be an interesting parameter for you to play with. If you make that value too high for a scout group, say you have 20 boids that are biased towards the right side of the screen, and you give them a 100% bias, what will happen when you say go is those 20 boids just leave, and they don't pull any boids with them. If it's somewhere gently in the middle, then what will happen instead is those boids will start to gently move this way, but they'll pull the whole group with them. And what we're going to be playing with is where exactly does one turn into the other? And then what we'll do is set up 2 scout groups, right? So you can have a bias group this way and a bias group this way, and see what happens when we play with these values and play with the sizes of each of those groups. Does the colony split? Do the bias boids just leave and leave the whole colony behind? Does one bias group win and the other bias group lose? And as I mentioned, for the 5730 students, I'll ask for that bias value to be dynamic. So it will also be updated every frame based on what the neighbors are doing. Okay. And then after going through this whole thing, the final thing that you'll do is you'll have some new x velocity and some new y velocity, and I'll ask you to enforce speed limits. A particular boid will not be allowed to exceed a particular speed or go slower than a particular speed. It can go in any direction, but it has to be going faster than some minimum speed and slower than some maximum speed. This just helps with the illusion. Having some range of speeds is nice because boids can catch up to other boids, and that kind of looks right. But if we don't do stuff like this, we can end up in situations where boids are just like screaming across the screen, which doesn't look organic, right? And having some minimum speed also kind of looks organic, because if you watch, I don't know, if you watch like a collection of starlings, they often gather over the baseball field in the evening. If you keep an eye out, you'll see them. And notice that there seems to be a minimum speed associated with them. And I haven't watched as many colonies of bees in flight, unfortunately. I'd really like to, but I just haven't been lucky enough. But I imagine that some similar effect is there as well, where there's some minimum speed associated with the bees. Okay, and then after all of this, right, so for a particular boid, at the start of that frame update, that boid has had some x and y position, it's had some x and y velocity, and then we've gone through this process for that particular boid of updating its velocity a little bit in order to move away from boids that are too close. So we've updated the velocity a little bit here according to the avoid factor. And then we've gone through and updated the velocity a little bit more according to the alignment contribution. We've updated the velocity again according to the cohesion rule. We've updated the velocity again to potentially turn around at screen edges. And then we've enforced speed limits on our velocities and perhaps introduced a bias. So by the end of this whole process, we have some new x and y velocity for that particular boid. And the last step is to use that new x and y velocity to update the x and y position of that boid. And doing so is really simple because of the units that we've chosen to represent position and velocity. Position we're tracking in pixels, velocities we're tracking in pixels per frame. So the new x and y position of that particular boid is equal to its old x and y position plus the new velocity that we've just calculated. That makes sense? This is an Euler integration, right? So this is the first term of a Taylor series expansion, where we're saying new position is equal to old position plus velocity times delta t. You would ordinarily see a delta t here. Because we've very cleverly chosen our time unit to be frames. Delta t is one frame. So our new x and y position is just equal to our old position plus the velocity, our updated velocities. So for each boid, the sequence of events will be, say I'm updating boid A. The first thing that I do is erase boid A. Erasing boid A is the same as drawing a black boid over where the boid was. That's erasing it, right? So incidentally, that's the fastest way to do erasing. It's tempting to just wipe the whole screen and then redraw the whole flock. If you do that, you end up with kind of a stuttery effect, a flickering effect on your flock. It's much smoother. It looks much better to your eye to erase a boid, update its velocity, use that velocity to update its position, and then redraw it at the new position, and then move on to the next boid. So 30 times a second, you are going through each boid, erasing it, redrawing it, erasing it, redrawing it, erasing it, redrawing it. By the time you've spent all 33rd and a third milliseconds associated with that 30 frame per second update, you will have erased and redrawn every boid in the flock, and then you go back to this first one, and you start erasing and redrawing it again. These are some parameter values that will get you started. These generate the flock behavior that we were looking at last time, and I think it looks nice and organic. You could play with this a little bit, and that would be fine. Let me just briefly talk through these to help you with, I think this will be helpful with debugging. So turn factor, that describes the radius of curvature when we leave the screen and come back. Make that really high, you get billiard balls. Make that 0, and the boid just flies off the screen and never comes home. Make it too small, and it has a really, really large radius of curvature. Visual range, measured in pixels, describes how far any particular boid can see. So if you use the default parameter settings here, any boid can see as far as 40 pixels in any direction. Can't see beyond that. Protected range describes how big each boid's personal space bubble is. I suggest 8 pixels. Looks kind of right. Centering factor describes the contribution to the velocity update that comes from tending towards the center of mass of the neighboring boids. You'll notice, incidentally, that the avoid factor and the matching factor, they're at around 0.05. Centering factor is much, much lower. This is only because, if you recall, when we're applying the centering rule here, we're looking at differences in position, which could be as high as, it's a 640 by 480 screen. So these differences could be in the hundreds of pixels, perhaps, or at least tens of pixels. Alternatively, or in contrast, if we look at, say, the alignment contribution, we're looking at velocities, which we're constraining to be much smaller numbers. These will be on the order of 1 to 3 pixels per frame. So there's a couple of orders of magnitude difference in the magnitude of the positions as opposed to the velocities. And that's why we see a couple of orders of magnitude difference in the sizes of the centering factor versus the avoid factor and the matching factor. Does that make sense? Because the positions are a couple of orders of magnitudes larger in size, we decrease the centering factor by a few orders of magnitude so that all these relative contributions are, nobody's overpowering anybody. They're all important, all of about equal importance. So this describes the tendency of each boid to move towards the center of mass of its neighboring boids. Turn this up really high, and you get what I think kind of looks like bugs. They all kind of go like this and go towards the center of mass of each other. Turn this towards low, and they'll be a little bit more disparate. Avoid factor describes the tendency for each boid to align with the direction of travel of its neighbors. Matching factor, that's the matching factor. The avoid factor describes the tendency for each boid to move away from boids that get too close. These are my suggestions for max speed and min speed. Okay, I was wrong. So I'm suggesting a max speed of 6 pixels per frame and a minimum speed of 3 pixels per frame. But because we're using fixed point arithmetic that has fractional resolution, a boid can have a speed of, a non-integer value between 3 and 6. I'm giving a suggestion here for the maximum amount of bias that you allow for a boid to have. And bias increment, we'll talk about this in a little bit, but this is for dynamic updating of that bias value. So what I'd like to do next is I'm going to walk through some pseudocode that describes each step of the algorithm that we just talked through, but does so a little bit more algorithmically than I just did. And then I want to look at the demo code for this week's checkout and talk about where this algorithm would get inserted in that code. Essentially, all of this is going to live in a thread that you make sure gets scheduled 30 times a second. And in that thread, you'll go through every boid, erase it, compute its new velocity, use its new velocity to update its position and redraw it. And then that thread will get rescheduled again. So let's look through this pseudocode. And by the way, there were some students last year, and I'm not saying any of you would have this philosophy, that saw this pseudocode and went, he gave us all the code. It's easy. What you will find is that this is tricky to implement. So the reason that I'm giving you all of this pseudocode is to help you with implementing this. But one of the other reasons that I like this lab is in addition to thinking about optimization here, the other thing that I hope you'll think about in this lab is writing code that you can debug. This is complicated, so I think it will behoove you to be thoughtful about which parts you implement first and how you test the implementation as you go, right? So I think it would probably be unwise to translate all this to C, slap it in a thread, and see how it works. Because debugging this is tricky. This particular algorithm, debugging it is tricky. I think probably a perhaps better way to go about this is to say, okay, let's just have our boids turn around at screen edges. Boids aren't going to know about each other yet. They're just going to turn around at the screen edges, and let's see if we get behavior that looks right. And then you say, okay, the turning around at edges contribution to the boid velocity seems to be working properly. And then you say, let's add a centering factor. Okay, one of the 3 contributions to boid updates. You add that, you ask yourself, what's the emergent behavior that I expect to see as a consequence of adding this? You see if you see that behavior, and then you add the next one. The other thing that you may want to do, and this is not a requirement of the lab, but it's something that you may thank yourself for doing, is you are asked to implement a user interface, and that user interface will allow for the user to do things like specify the boundary conditions for the flock. Do we want them turning around at all the edges? Do we want them to march up and down the screen? It also allows for you to do things like set how many boids are in each scout group and what's their bias values. You might consider adding to that user interface, just for making your program more debuggable, the ability to change things like the centering factor, the matching factor, and the avoid factor. Because then you implement all this, you get the flock running, and it's behaving weird. You could say, okay, let's just make the matching factor 0 and see if now it looks more normal. And then we can isolate wherever our bug is to somewhere associated with the matching factor. So this is what I mean about trying to write code, being thoughtful to debugging that code as you go. So let's look through this pseudocode. So for each boid, you will start by zeroing all of those variables that we talked about previously. So you're going to zero variables that you might call x position average and y position average. These will be used in the centering factor contribution to the velocity update. Velocity averages, those will be used in the alignment. The number of neighboring boids, and the close dx, close dy, which will be used in the protected range contribution to the velocity update. And then for each boid, you look at every other boid, and you compute the difference in your own x position and that other boid's x position, and your own y position and that other boid's y position. You then ask yourself, is the absolute value of that difference in x positions less than the visual range? and likewise is the absolute value of that difference in y positions less than the visual range. The reason, incidentally, for doing that check is a little bit subtle. We're using fixed point arithmetic, fixed point data type to keep track of our position and velocities. If we're not careful, we could overflow that. So before computing the squared distance between us and that other boid, we want to make sure that this line of code isn't going to overflow our data type. If both of those differences are less than the visual range, then we can be confident that we aren't going to overflow the data type. If we don't do that check, and we have two boids that are on opposite sides of the screen, so they have a huge difference in x and y positions, and then we compute their squared separation, that's going to overflow the data type, and the CPU is going to think that they're actually very close to one another, and we're going to get weird behavior in the flock. So we do this check first. We then compute the squared distance that separates them. So if we wanted the distance, it would be the root sum of squares of dx and dy. No reason to do the square root. We'll just work with the squares of the distance. So we compute the squared distance that separates us. And then we ask, is the distance that separates us from that other boid less than our protected range? More specifically, is the square of the distance that separates us from that other boid less than the square of our protected range? If so, just like we talked about earlier, we increment close dx and close dy by the difference between our position and that other boid's position in x and y. Alternatively, suppose the distance that separates us isn't less than the protected range. We then ask, okay, well, is it less than the visual range? Which is further. In the event that it's less than the visual range, we increment the x and y average positions by the other boid's position. We increment their x and y average velocity values by the other boid's velocity, and we increment the number of neighboring boids by 1. We found a neighboring boid. Then, in the event that we have any neighboring boids at all, we divide all those accumulating variables storing the positions and velocities of our neighbors by the number of neighbors that we have. This is computing the average position and the average velocity of our neighbors. And then we update we do the centering factor and matching factor updates to our velocity. So we say our new x velocity is equal to our old x velocity plus the difference between the average x position and our position multiplied by the centering factor plus the difference between the average x velocity of our neighbors and our own x velocity multiplied by the matching factor. And same story for y. And then after doing that, we do the avoid factor update to the velocity. The reason that this is outside of this conditional is it is possible that we have no neighboring boids. That is to say, no boids that are outside of our protected range but inside of our visual range. But we do, in fact, have boids that are inside of our protected range. Right? So this lives outside of this conditional. We then check to see if we have gone outside any of our margins and if we need to start turning that boid around. If we've gone outside the top margin, then we increase our y velocity a little bit. Remember that y increases down on a VGA screen. Pixel 0, 0 is the upper left corner. X increases. Pixel 0, 0 is up there. X increases that way. Y increases that way. So if we go above the top margin, we increase our y velocity, which is to say we start to point the boid back down towards the bottom of the screen. And a similar story for all the other margins. And we modify the velocities by that turn factor. There's a little section of pseudocode here that describes how, if you're in 5730, you will dynamically update the bias value. You'll do so by looking at your preferred direction of travel and the direction that you are presently traveling. If you're moving in the way that you want to move, you increase your amount of bias in moving that direction. If you find yourself moving opposite to the direction that you want to move, you start to give up. You decrease your bias. But everyone will have some bias, the ability to bias some subset of the group, and you will implement that bias in the way that I described earlier. After you've gone through and updated your x and y velocities, if that particular boid has a bias value, you then say, okay, I'm going to update the velocity again, and my new x velocity is going to be equal to 1 minus my bias value, some number between 0 and 1, times the x velocity that I just calculated. If this is 0, then I just retain my previously calculated x velocity. If it's 1, then my new x velocity just becomes, in this case, 1. Preference towards the right side of the screen. Or alternatively, if I'm in the group that wants to go this way, then I would get a bias in the -1 direction, this side of the screen. You compute your speed by taking the root sum of squares in your x and y velocities. Remember in the FFT, when we were calculating the magnitude of the FFT output? Remember the FFT output's a complex number, real part and imaginary part. To compute the power spectrum, we wanted the root sum of squares of the real and imaginary parts. And we used that little trick, the alpha max plus beta min algorithm, that approximated the root sum of squares by doing some parameter times the maximum between, in our case, the x and y velocities, and some other parameter times the minimum between those two values. Here would be a good place to implement that, right? That'll save you some CPU time. So in any case, you compute or approximate your speed, and then you ask, am I less than the min speed? In which case, I'm going to speed up a little bit in the same direction that I'm going. Am I greater than the max speed? In that case, I'm going to slow down a little bit, but maintaining my direction of travel. All of this has updated our x and y velocities, and then at the last step, we update our positions. With our new positions, we redraw that particular boid, and then we go on to the next boid and do the same thing. What do people think? Yeah.
For the calculations, could you use the position of all the boids at the beginning of the frame rather than like using their updated positions like after you do each calculation?
So are you asking whether you can do each boid's updates based on where every boid was at the start of the frame as opposed to, you know, updating boid C based on boid A's update? So you could, but it's not obvious to me that that gives you any advantage. I think it would require that you save more state per boid. I think because then you need for each boid you need new position, old position. I think.
Well, you would know like all the neighbors for each boid at the beginning of the frame.
Maybe.
Okay.
Maybe. Yeah. Let me say this. I think if you implemented it in that way, the illusion would still hold. It's not obvious to me that implementing it in that way gives you an advantage, but just because it's not obvious to me doesn't mean that it doesn't. It just might mean that I'm not thinking about it correctly at the moment.
So is it fine to do like the calculation like twice per boid for each frame, because like it could shift and be like someone's neighbor and then now it's not their neighbor anymore? I don't know.
So let me see if I can so suppose we update boid A, and in updating boid A, boid C was in the visual range, so boid C contributed to boid A's update. And then we get to boid C, and for boid C, boid A has moved out of its visual range. That is an interesting observation. It's not something that I've accounted for here. It doesn't harm the illusion, at least as far as I can tell. I suppose okay, let me answer in the following way. If you accounted for that, perhaps that maps better to nature, in the sense that in all likelihood, if those were birds, both would react to one another if they could see one another. However, for purposes of this lab, where the objective is create an illusion that tricks your brain, not accounting for that, in my experience and based on my own experimentation, doesn't affect the illusion. We can't tell that boid C isn't looking at boid A. So maybe it's a cheat. Maybe you'd put that in the cheat category, but it's an okay one. Other questions? Yeah.
I feel like we can use one more piece of information we didn't use. One is that we are able to maintain the array of the position of each boid, so that if we use this information, we are able to calculate or we could predict the next position of the boid. So, for example, if the goal is to achieve 30 hertz, we can downgrade it to 15 hertz, but using those array to predict the intermediate value, that's similar to do a sort of, if put it in a naive way, it would be like a regression that using those data points to draw a line, and you can use the value on the line to create a more smooth 30 hertz movement, only with 15 hertz information.
So let me see if I understand your suggestion properly. Are you suggesting that suppose we had knowledge of the state of the flock at, time 0, then that gives us a pretty good guess of what the state of the flock will be at time 1. That is to say, suppose we know we have gone through and we've sorted the boids and we know all the neighbors. That gives us a good starting guess for the neighbors in the next frame. Is that the suggestion?
It's basically using memory to exchange time. So, for example, we have position of boid A at time 0, 1, 2, 3, and we can able to get a pretty good guess of the boid at position 4 using the previous precision.
So it's a reasonable suggestion. What this whole lab is about is evaluating the trade-offs. So implementing that costs you something. Is it worth what it costs? And in that case, it certainly might be, right? But this is what we're trying to figure out for each potential strategy is, one strategy is, well, suppose before each frame we sorted all the boids so that they're all sorted by X and Y. That makes knowing which boids are neighbors to other boids considerably easier. But is that worth it for the expense of the sorting algorithm? And I know that's not what you're suggesting, but this is the sort of thought process that's going in here is the advantage that getting some sort of information or getting the system in some state worth the cost of getting that information?
To give a brief idea, how would you implement the search algorithm where the naive way was looping all the possible.
Folks, we're out of time. If you want to get out of here, I'll stick around a little bit, but don't feel any obligation to stay.